it's coming.
Okay, we're going to talk further about capacitor networks. In particular, we're going to talk about equivalent capacitance. So yesterday we talked about two main ways that capacitors can be connected. Rather than draw it, I'll have you draw it. I'd like for each of you to draw two capacitors in parallel. I've given you a power supply to get you started.
I was going to my backpack looking for these statement for English, and I found this mysterious letter from child
Wait, what's your name?
We only have 30 minutes, so I'm going to ask you to focus in.
This is right. I figured on the script calculator. So
Okay. Yeah.
I started drawing it all day, so I was like, might as well finish.
And you can draw your capacitors in several possible ways. You can draw them like this, C1 and C2. You could also draw them like this. Or you could even draw them, oddly enough, like this.
Wow. Can I say this about a series?
Okay. So what is it about these that makes them all in parallel?
They're all parallel.
In what way? Why?
They both have positive and negative straight from the power.
If one of them shuts off, then it.
That's pretty close to true. You're on the right track.
A direct
It's like they're organized like this.
They're all connected.
They're not dependent on each other?
Nope. How about this? They are connected to each other at both ends. That's what it means to be parallel.
I knew that like they were like this, not like this.
So, Alex, actually, that is incorrect. And we're going to make sure that we do not get that confused here. Sorry. Actually, this circuit right here would not even qualify as parallel. It would qualify as being disconnected. Because here, both of these are connected. Yeah, this isn't going to work.
Wouldn't it have to be connected to the right of C2?
Yeah, we're going to have to do it like this. Let's see. C1, C2. I could be a little narrow, stand to be a little narrower. And we're going to have to do something like that and something like that. There. That's better. It's kind of crazy, but it's better.
What was the point?
Well, right. I would never draw it like this. My whole point is this, that what makes them parallel is not how the elements are physically arranged, it's how they're connected. It's connection, not orientation. That's exactly it. So if you see here, the blue lines connect C1 to C2, just like so. And now the green lines here connect C1 to C2 on the other side. And as a result, they are in parallel because they're connected on both sides. Ta-da.
So as long as the line, like the horizontal line next to C1 at the top one, like those lines just have to be touching.
Just look at how they're connected. If they're connected at both ends, they're parallel.
So wait, how's the top one connected?
What do you mean, how's the top one connected?
You scroll.
Wait, can you draw a series right next to one of those just so I can see the difference?
I will on the next page, yeah.
There we go.
Well, can you draw it next to it so I can see the difference, like one person?
Okay, well, give me a moment to do that parallel because we're going to send that out. So, and then the characteristic about parallel capacitors is that in parallel, we say that the voltage is the same. for both, and the charges add together, meaning that the total charge is the charge on one plus the charge on the other. And so we like that. Now, how does series look like? Everybody draw for yourself two capacitors in series. Go. And you should have something that looks like this. Or it could look like this. Or it could even look like this. What makes all of these three be in series? You're not connected at both ends. No.
It's just like,
What do you listen for? You got stuff less.
can you go back to parallel?
Sure.
Because they're actually connected with one.
They're only connected on one side.
They're connected on one end. Exactly right. That's half of it. The other half is
Voltage is different.
the connection between them has no branches coming off. See that connection right there? It's a straight shot from C1 to C2. And there are no other additional wires or circuit elements coming off between them. That's what makes them be in series. No matter how they're arranged. So if you look at this, please do not look at that and say, oh look, they're in parallel, because I see parallel lines or something. You have to look at the connections. How they're connected, not how they're oriented. Is everybody clear on that?
You're gonna make it like really crazy funky on the test. Or like really
Just for you. I'll say, everybody else gets to do this simple circuit. Alexis, here's your circuit. And then I'll just have it be equivalent to the other one. And you can figure it out. Okay, so what did we say about capacitors in series? Voltages are add, yep, and charges are the same. Good. Very good. So I would, instead of writing Q1 and Q2 here, I'd write Q for both. And I would say that there is a voltage drop V1 and a voltage drop V2, and V1 plus V2 has to equal the total on the power supply, just like that. And so that's series and parallel capacitors. Now, let's put some numbers to this and see what happens, and we'll talk about equivalent capacitance. Suppose that I've got a 12-volt power supply, and I'm going to take and put it in connection with two capacitors in parallel. A 100 microfarad capacitor, C1, and a 200 microfarad capacitor, C2. And now I'm going to ask a simple question: how much total charge is stored? How much total charge is stored between these? Okay. Well, first I identify what is the configuration between them, and so I look at the connections and I see that they are in parallel because they are connected at both ends. Okay, so that's the first thing. And now I remember what I remember about parallel. Voltage is the same, charge is added. And so I can immediately say that for this guy the voltage drop is 12. For this guy the voltage drop is also 12 because the voltage has to be the same as what it's connected to, the power supply right there. And for each capacitor then, Q equals CV, so Q1 equals C1V, and Q2 equals C2V, and that's equal to 100 microfarads times 12 volts. And this is 200 microfarads times 12 volts, and I'm not going to be fancy, I'm just going to keep it in terms of microcoulombs. 100 times 12 is 2400 microcoulombs charge stored on this one. And, no, sorry, 1200 microcoulombs stored on that one. 2400 stored on the other one. There we go. That's better. And now if I want the total, because again we are in parallel, then the total is equal to Q1 plus Q2, which is going to be 3600 microcoulombs. See, very straightforward. I computed the charge of one, charge of the other, they add together because they were. Now, an engineer comes along, you know the joke, right? The optimist sees the glass as half full. The pessimist sees the glass as half empty. The engineer sees a glass that's 2 times the size requirement. So the engineer comes along, he says it's wasteful to have 2 capacitors storing this charge here. We should be able to take those 2 capacitors out and put it in with 1 capacitor that can store the same charge at the same voltage. An equivalent capacitor. In other words, we ought to be able to transform our circuit into a circuit with a 12-volt power supply and an equivalent capacitor that does the same job as both of these put together. Okay. So to do that, it has to store the same charge. In other words, Q total has to equal CEQ times V. And I already know the Q total, which is 3600 microcoulombs. And I know the voltage, of course, which is 12 volts. So that CEQ is going to be, let's see here, what's 3600 divided by 12? 300. And what's a microcoulomb divided by a volt anyway? Not a farad, but a microfarad, exactly. So that my equivalent capacitance is 300 microfarads, just like so. What do you notice about the 300? Yeah, it looks like it's the sum of the 100 plus the 200. I strongly suspect that the way we go about doing equivalent capacitances in parallel is you just add them together. So to prove that, I need to generalize what I did here. I need to do the same operations, but I need to do them with C1 and C2 instead of 100 and 200. So let's do that. We'll construct for ourselves a circuit that has a power supply V and a capacitor C1 in parallel with a capacitor C2. And we're going to do the same thought process that we just did. We're going to compute the total charge, and then we're going to set total charge equal to CEQ times V. So I say that Q1 is equal to C1 times V, and Q2 is equal to C2 times V, so that the total charge is equal to C1V plus C2V, and that must also equal CEQ times V for my equivalent circuit right here. Well, do you see what I see? What do you see? It's exactly right. Common factor of V. And in the other class, they observed also that there's a common factor of 1, so there you go. It was Charles something saying, you know.
Shockingly.
Wait, what did he say?
We were joking around. He said, hey, look, there's a common factor of 1. Which is true.
He's not wrong.
So we have then the equivalent capacitance for parallel capacitors. Or we'll call it parallel equivalent capacitance. And it's delightfully simple. CQ is simply the sum C1 plus C2. Okay. What's that?
It's the outer both sides.
Yeah.
1, 2.
Equals EQ.
1 EQ.
Okay. Well, that was successful, so we wonder what happens if we do it in series. And when we do it in series, we're going to have to do a little bit more math, but we're going to end up with a similar formula that is going to be the equivalent capacitance for series capacitors. So let's see how this goes. Let's take our 12-volt power supply and hook it back up to the 100 and 200. But this time, we're going to place them in series. And how do I know they're in series?
Only one touching, and there's nothing coming out of what's in it.
There's nothing coming out. That's very good. That's right. Connected at one end, nothing coming out of that connection. There. And so now what I'd like to do is I'd like to find out how much charge is stored. But this is a little bit different because when capacitors are in series, they have the same charge and their voltages add together. In other words, this is no longer 12 volts. This is going to be some voltage V1, and that's going to be some voltage V2, and V1 plus V2 is going to add up to 12. Just like that.
I hope they each independently add 12.
No, they don't.
Is that only
independently
with
add 12.
parallel with each?
Exactly. Because the parallel were tied at both ends, they had to have the same voltage drop.
So adding doesn't mean that they're each 12 being added. It means that they add to 12.
Correct.
That's
Right. Yeah, glad you asked that question. So adding does not mean that the total is 24. Now, if you think about it in terms of like height, what we're doing in series is we're taking these two capacitors and they are each one dropping down a certain amount. And the total has to add up to the 12 here. Does that make sense? Whereas in parallel, each one was dropping the 12 independently. Okay. So now, what is this V1 and what is this V2? Well, I don't know the amount of charge, but I do know that Q is equal to CV, right? So Q is equal to C1V1, and it is also equal to C2V2. And that means that I can replace V1 with Q over C1, or Q over 100, and I can replace V2 with Q over C2, which is Q over 200, and that's equal to 12. And there you go. Well, now this is an equation that involves our favorite thing, fractions. And so we wonder how to deal with the fractions, and of course we deal with the fractions the same way we always do. We clear the fractions by multiplying both sides by the I can do that. The same thing is the least common multiple, also known affectionately as the least common denominator. Right? And what is the least common denominator of 100 and 200? Not the least common factor, not the greatest common factor, the least common multiple. 200. Right. If I were to combine the fractions, I would still need the least common denominator, and then I would end up needing to multiply it and a cross multiplying separately.
I think I would just add them together and then multiply each separately. Then you have 3 Q equals, which is what you have.
Right. So, when I multiply here, then I cancel. 200 divided by 100 is 2, and 200 divided by 200 is 1. And on this side, I get 2400. So we get 3Q is equal to 2400. This is microcoulombs here, because it is microfarads times volts. And so Q is equal to 800 microcoulombs. Now, this math was a little bit more involved in the previous process, wasn't it? So we're going to probably want to come back and come up with a formula for this. If I go back to my 800 microcoulombs and I put it back into the capacitor here, I can now calculate the voltages separately. Because Q is equal to CV, or in other words, V is equal to, V1 is Q over 100, then Q is 800 over 100, which is 8 volts. V1 is equal to 8 volts. And Q2 is equal to, sorry, V2 is equal to Q over 200, which is 4 volts. And voila, they add up to 12. See? Cool. But a little bit more work. Now, I want you to notice some things that are not intuitive about capacitors in series. First thing, that charge that we have there, that 800 microcoulomb charge, is a whole lot less than when we had it in parallel. When we had the two capacitors, same two capacitors in parallel, they stored up 3,600 microcoulombs of charge. Now, by putting them in series, I store only 800. And that's because the two of them have to share a total of 12 volts each. That's the first thing. The second thing that I want you to observe is which capacitor got the larger voltage drop? The smaller capacitor. That's exactly right. And that's because the charge had to be the same for both, which means that capacitance and voltage are inversely related for a given charge. Does everybody see that? So that's not intuitive. I stick up this network, and you might think at first that the 200 would get the larger voltage because it is the larger capacitor, but in fact the inverse is true. Okay?
But explain why.
Yep. They both have to have the same charge. So Q is equal to C1V1 and equal to C2V2. Because these are multiplied together, that's an inverse relationship. If C is bigger, V is smaller, necessarily.
So if C was 1, then V would just be U.
Yeah, if C was 1, then V would be basically 12, and we get nothing in that one. Practically nothing in that one. Okay? Well, what about our equivalent capacitance idea? What if I wanted to take my two capacitors out of the circuit and replace them with a CEQ? What I require in that case is that, oh, stop it. There we go. That Q is equal to CEQ times the voltage, or CEQ times 12. And I already know how much charge is stored. That's 800 microcoulombs. So that CEQ is equal to 800 over 12, which is the same as 800 over 12 is the same as 200 over 3, right? Which is 66.7 microfarads. And so we find another surprise about our equivalent capacitor, and that is that it is smaller than both the 100 and the 200. Why? It can be smaller because it only has to store 800 microcoulombs of charge at 12 volts, whereas my other two capacitors had to store them at 8 volts and 4 volts respectively, right? And so they needed to be larger in order to do that. Okay. Well, this calculation was kind of involved, and so we'd like to turn it into a formula. Let's do this whole thing all over again, but this time with C1 and C2 instead of 100 and 200. So our setup is going to be power supply B, C1 in series with C2, and what we'd like to do is to turn that into a circuit with an equivalent capacitance that stores the same amount of charge. And so here we go. We know that there's going to be a voltage drop V1 and a voltage drop V2 that add together to give the total, because that's what voltages do for series capacitors. And we also know that the charge is going to be the same for both. C1 times V1 and C2 times V2. So in other words, V1 is Q over C1 and V2 is Q over C2. And so now I can replace right here with Q over C1 plus Q over C2. Now what about the V? Over here, I can say that Q, again the same charge as is stored here and here, is equal to CEQ times V. So that V is equal to Q over CEQ. What do you see? A lot of Q's. A common factor of Q, in fact. And when I factor out that common factor and cancel it, I arrive at a relationship that is called the equivalent capacitance for series capacitors, or the series equivalent capacitance. Now, some things to know about this. First of all, naive and poorly prepared algebra students will say, oh, I can just go through and flip every term, so CEQ equals C1 plus C2. No, wrong. To combine those on the left-hand side, you need a common denominator, right? At least common multiple of the C1 and the C2. In fact, if we do that, if I get a common denominator and combine them, then what I end up with is that 1 over CEQ is equal to all of this, so that CEQ is equal to the product over the sum. I'll just write that as C1 plus C2. But I don't recommend memorizing this formula for the simple reason that if I now have 3 or more capacitors in series, then it gets kind of ugly, whereas the first formula can be extended simply. 1 over CEQ equals 1 over C1, plus 1 over C2, plus 1 over C3, plus 5. Let's do an example, so you can see that this is not as intimidating as it seems. Suppose I have a 50 microfarad and a 40 microfarad capacitor. And what I'd like to do is to replace them with an equivalent. Just like that. And so I'm going to write it. CEQ is 1 over CEQ is 1 over C1 plus 1 over C2, just like so. And therefore 1 over CEQ is equal to 1 over 40 plus 1 over 50. Now some people are very comfortable doing this in terms of fractions. That's perfectly fine with me. But if you prefer to do it on the calculator, then it would look something like this. You do 1 over 1 divided by 40 plus 1 divided by 50 is that my CEQ? No, it is the reciprocal of my CEQ. CEQ is going to be 1 over that, which is 22.2 microfarads. And all you have to write really is this. And as noted before, the equivalent capacitance of my series is always less than either one of its components. And the reason for that is really simple. It stores Q at a higher voltage as compared to the other two. Yes?
Can we just leave it in the fraction form?
Sure.
Which would be 200.
Unless you have to worry about sig figs, so there's that.
So wait, if you have to worry about sig figs, fractions too exact.
Fractions to exact, right? All right, before you leave, do one. Find the equivalent capacitance of 150 and 20 microfarads in series. Go. I agree.
Probably about 18, 17.8.
Don't go away just yet. 17.6. Microfarads. All right. Now, all of you in your heads, find the equivalent capacitance of these two in parallel.
170.
170. The end. Yep.
Wait, we got to say?
Clearly,